helping you with Acorn and RISC OS computing.
Okay, so you can see the Lander theme talk title, can you? And can you see me alongside it? Great. All right. Well, I'll kick off then. Thanks very much. Right. Well, tonight I'm going to talk to you about Lander, which I probably don't need to explain to anybody in this group what Lander is, because you have RISC OS in your title, and of course Lander is very much associated with Arthur and RISC OS at the start. But I'll run through the first slide anyway, which explains what Lander is. I mean, personally, I started playing Lander in 1989 when I got my Archimedes A410/1, which is behind me now, and didn't really get very far with Lander because it is a brutally difficult game to play, famously difficult. But I did a lot of crashing and staring at the wonderful graphics and basically thoroughly enjoying what is still an astonishing graphical playing experience. But in recent years, it's become more interesting to me because it's basically what David Braben did next after co-writing Elite with Ian Bell. They'd converted Elite to all the different platforms and all the different home computers, and in 1986 were toying with Elite 2. And one of the things that Braben was looking into were landscapes for landing on planets as part of Elite. And you can sort of see the connection when you see Lander, because it's all about landscapes and flying above it and crashing into the landscape is a very popular pastime in Lander. But you can sort of see how it would have fitted into Elite. But in the end, it didn't make it into Elite 2 because Elite 2 didn't really happen on the BBC Micro and so on, and actually happened on the PC a number of years later. But Lander is a 3D scrolling landscape shooter with beautiful, solid 3D graphics. It is the first ever game for the ARM platform. And it was written in late 86, early 1987, in about 2 months, according to Braben. He started work on it on an ARM evaluation system hooked up to a BBC Micro. So that's as a second processor sitting alongside the BBC, which would be used for the input and output. But actually, he said at the time that it couldn't really do much greater with it because the graphics weren't up to scratch. So he was basically thinking in terms of algorithms for Elite in the BBC way. But then Acorn lent him a prototype A500, which was the prototype of what became the first Archimedes, the A305 and A310 and A440. And that was in early 87. And he finished off Lander on that. Even though apparently the disk drive didn't work on the system he had, so he still had to develop the code on the BBC Micro and get it across somehow. I mean, honestly, the hurdles for creating this game are mind-boggling. But it was only 2 months' work, and it was written in the BBC Basic assembler, which was also on the BBC Micro and got carried across to the Archimedes. I believe it was, because I've seen snippets of the source code on various videos on YouTube. Haven't actually seen the source code for Lander because it's never been released. But anyway, he finished Lander after a couple of months, and it was then bundled free with Arthur, the first operating system for the Archimedes, and later on RISC OS 2, which came out in 1989. It didn't get bundled with RISC OS 3. And indeed does work on RISC OS 3, but doesn't work on RISC OS 3.5 and later, so it won't run on a RISC PC, sadly. Lander led to Zarch, which was the commercial game that Braben turned it into. And Zarch is a much more polished commercial game. It's basically the main differences are that the edges of the square landscape on Lander are whole blocks. So as you scroll over the landscape, fly over the landscape, the blocks jump into being on the edge. So it's a bit of a juddery experience. But Zarch extends the landscape so that it overlaps the edge of the screen. So it's a smooth process. So that makes quite a big difference. But Zarch is also much more of a game in terms of it has a lot more 3D objects flying around. It has enemy spaceships that you can fight. It has a radar in the top left of the screen. Has a whole kind of virus concept where enemies are polluting the landscape by turning it red by dropping virus bombs on it, and so you try to save the world by killing off the enemies. It also has a self-played demo. But Lander is known really as a demo version of Zarch, but I think that's rather unfair. Lander is a game in its own right. It just doesn't have all these extra features. In fact, it also has some features that are exclusive to Lander. For example, if you ever reach a score of 800, which I've never done, you start at 500 and you need another 300 points for that. But at that point, 3D rocks fall from the sky, and the higher your score, the more rocks appear, and you have to dodge them, which is quite fun. And that feature doesn't exist in Zarch. There's also a hover mode in Lander, which you can use. I think it's the middle button for hover, and the right button is for full thrust. But in Zarch, they used the middle button for dropping bombs. So obviously they took that feature out. So that's a Lander exclusive. And another exclusive Lander feature is that if you remotely touch the mouse when you're on the launch pad, you die and explode in a massive shower of particles, which is something we're all very familiar with if you've ever played Lander. And Zarch, you can only die once you've actually taken off, which is slightly kinder. If I show you a comparison of the starting screens in Lander and Zarch, Lander is on the left and Zarch is on the right. You can see that they're clearly coming from the same code base here, really. Zarch has a differently shaped landscape, various new features, like it's got a rotating radar thing next to the launch pad there. And you can see the radar on the top left and a rather nicer graphical high score thing along the top, whereas Lander is, got some text along the top and a slightly different structure on screen, but it's basically the same game, and indeed the code underneath it is very much the same. It's just Zarch has been expanded into a fuller game, and in fact the same. I've got a copy of Zarch here, which I bought back in the day. Lovely little thing, and the same engine was used for Conqueror, which I also bought back in the day. So it's a 3D landscape groupie, and this is a tank game on the same landscape, where the game part was written by Jonathan Griffiths, who had done lots of great BBC micro games. So, the code lived on, but it started with Lander. And I'm going to talk about Lander today because that's the game that I've analysed. So here's what I'm going to cover today. I'm going to talk quickly about the Lander documentation project, which I did recently, beginning of this year, and which has led to this talk. I'll then talk about the 3D landscape, which is procedurally generated. Of course, this is a David Braben game. Of course, it's procedurally generated. And I'll talk about how that's done. I'll talk about the 3D objects. So that's trees and our ship and the rocks falling from the sky and all that sort of thing. I'll talk about particles and particle clouds, which are how explosions and splashes and things appear on screen. I'll talk about depth sorting objects, which is how the code knows what to draw and when, so that everything is correctly ordered on the screen. So things that are objects that are in front of other objects do actually get drawn in front of them, and how the code is rather cleverly written to make that a quick process. I'll then explain how the mouse flight process works, and which is quite useful if you've ever actually, well, if you want to be slightly better at this, it helps to know how it works. It doesn't necessarily make you a better player. I'm still not very good, but at least I know why I'm rubbish, rather than just wondering what on earth is going on. So I'll explain how that works. And I'll touch on Lander's origins on the ARM1 in the ARM evaluation system and what that meant for the code. And finally, I'll show you Big Lander, or show you screenshots of Big Lander, because again, I'm not very good at playing this game, which is a version of Lander that I built with a massive landscape. So it's just tweaking the code so that instead of it being 12 by 8 tiles, it goes up to 121 by 121 tiles, and it's really quite impressive. Okay, so let's start with a quick look at the Lander documentation project, which I did earlier this year. I've documented in the past Elite, Revs, and Aviator on the BBC Micro, and Lander, of course, is on the Archimedes, so it's a completely different instruction set, but it's the same sort of approaches that I learned in analysing the BBC games could be applied to Lander. So luckily, Lander, it comes in two flavours. There's the version on the Arthur app disk, and the welcome disk, I think it was called back then, and the version on the RISC OS applications disks. Now, they are exactly the same game, exactly the same binaries. However, the RISC OS one is encrypted. So I didn't touch that one. I broke the encryption on it to prove that it has the exact same binary as the Arthur one, but instead I took the Arthur binary and worked with that because encryption is just a speed bump on the way to getting at the code. So I took the Arthur binary and disassembled that using a Python script from the web, which just as a one-off run to point it at the binary and produce a textual disassembly listing. I then built a build pipeline using the VASM assembler and some Python scripts I wanted to build this project using a RISC OS style of source code. So really close to the BBC Basic, the original BBC Basic assembler dialect, rather than, doing it in a kind of more modern ARM type thing. So I'm using VASM, which is a modern assembler, but I wrote a bunch of Python scripts to convert essentially from BBC Basic assembler into a VASM compatible dialect and build that. So that's the end of that part, was to have a source code, no sort of commentary or anything, but at least it was building a binary that was exactly the same as the version from the Arthur disks. Then I got stuck into it and started adding labels and documentation, just using a text editor, checking all the time that I hadn't broken it and was still building the same binary. And I built in a tool, a step that would deploy the final binary into Archimedes Live, which is a web version of the early Archimedes. Very clever stuff, a bit like JSB for the BBC Micro. I'm on a Mac, so there aren't so many Archimedes emulators. Arculator's one of the more popular ones, but that's PC and Ubuntu only, I think. So it's I did it via the website, the Archimedes Live website, and turned to my PC if I needed to analyze things in a bit more detail. From that as well, I built scripts to auto-generate a website with all of the documented source code in the same way as I did for Elite and Revs and Aviators. So the end result was a website with the fully documented, fully buildable source code for Lambda. I wrote more than 20 deep dives into how this works, which is kind of what I'm talking about tonight. And I also added a script that would produce a text file that you can copy to an Archimedes, load into Edit, save out as a basic file, run it, and that will compile Lambda on an Archimedes. So this is not just modern stuff. It produces real, proper RISC OS compatible source code in BBC Basic, which is great. So that was probably the first time that Lambda had been compiled on real silicon since Braden was doing it back in 1987, I would have thought. So that's quite entertaining. So that's the project, and I'll give you the URLs at the end of the talk. But let's have a look at some of the more interesting aspects of Lambda. So we'll start with the 3D landscape. And the 3D landscape is absolutely key to why Lambda is such a beautiful looking game. Here's a typical shot of Lambda. You can see this is wonderful sort of green and brown bucolic landscape with trees on it. I actually kind of prefer the feeling of Lambda because the landscape it stays green and lovely and kind of peaceful, whereas obviously in Zarch it's all being infected by aliens dropping nasty red viruses on it. But flying over Lambda is quite a peaceful and enjoyable process until you inevitably hit the ground. But it's slick, it's fast, and it's very impressive. Just to give you an idea of what the landscape really looks like, here's a shot of Big Lambda, which is the version where I made up to the size of the landscape. So this is 121 by 121, and that's what the landscape looks like in the game. But it's surprisingly, I mean, the Archimedes came out with loads more memory than the BBC Micro. The BBC Micro obviously was a 32K computer. The Master 128 was 128K. But I mean, the base, the cheapest Archimedes computer came with 512K, which is a good 5 times the, four times, yeah, 4 times the master. That sounded like an awful lot at the time, but memory is incredibly tight in if you're trying to run Lambda on an A305. So we've got 512K. The screen memory uses 160K. It uses 2 banks of 80K each and uses bank switching for smooth animation between frames. So that's 160K out the window. The system workspace always uses the first 32K of memory in an Archimedes. You've then got 32K minimum for the system heap and the supervisor stack. There's another 32K for what it's called cursor/system space/sound DMA in the manual. Not quite sure what that's about, but it's 32K that we've lost again. And Lambda itself requires 172K for the game code, variable storage, and all that stuff. So that only leaves 84K, and that has to have all the relocatable modules loaded into it, fonts, RAM disk, sprites. That's not a great deal. You can't really run a desktop with 84K. So if you want to run Lambda on an A305, you need to run a program called UseGame first, which unplugs all of the font and window managers and disables the desktop, and then Lambda will just fit. So even though, if we had a bigger machine, we might be able to store a really large landscape. The fact is that memory is tight, and there's no way that we could store a huge landscape in memory. So obviously, this being David Braben, it's procedurally generated. This is something that was a real key aspect of Elite back in the day, where the 2000 systems in Elite were procedurally generated from a tiny micro, BBC Micro, and that was a really important part of what blew people's minds. It created an open world. So of course he thought, well, let's do the same with Lambda. So just to look at what say we had, if we weren't using procedural generation, say we had a 256 by 256 tile landscape. That would take 65,536 values for each of the heights at each of the tile corners. If we coded them with a 1-byte altitude between 0 and 255, that would be 64K gone, and we don't have 64K spare in Lambda. And if we wanted 32-bit altitudes, that would be 256K. I mean, that's just not going to happen in a 512K machine. Lambda actually implements an infinite landscape with 32-bit altitudes. And it does this using a routine called getLandscapeAltitude. I should point out that all of the routine names are my own invention here, because I obviously don't know what they were in the original source code. But I called it getLandscapeAltitude because this routine gets the landscape at the altitude at a certain point on the landscape. And I'll show you how that works in a second. That's only 46 instructions. And each instruction in the ARM is 32 bits or 4 bytes. So that's 184 bytes of code. It has a lookup table for calculating sine, and that's 4,096 bytes or 4K. So that's a total of 4,280 bytes, which is considerably less than the 256K it would be for a finite landscape. And remember, this thing generates an infinite landscape, and it only uses lookup tables, shifts, and addition. So it's a very quick process. So I'm just going to explain to you now what this algorithm is. It's going to be interesting because it's quite gnarly, but here goes anyway. So it's all based on sine waves, and this is a sine wave. This is actually the contents of the sine table from Lambda put into Excel and drawn. So you can see it's a nice smooth sine wave. So this is a sine wave. The entire landscape is based on sine waves. It's a bit like it's actually uses something called Fourier synthesis, which is the other. It goes hand in hand with Fourier analysis. Fourier analysis, you may know, is the art of taking an arbitrary wave like a sound wave or part of a video signal and breaking that down into a combination of trigonometric functions, typically sine waves. And this is how stuff like image processing and sound processing works. Fourier synthesis is the opposite. It's taking a bunch of trigonometric functions and building a wave from it. So that's what the code does in Lambda. And it does it by adding together sine waves. So this is the algorithm that generates the landscape in lambda. And you can see it's a bit hard to see there possibly, but it is a sum of sines. Some of them are multiplied by 2. The sines take x and z as arguments. And just to point out that the coordinate system in lambda is 3D, so it's x, y, and z. And x is from left to right across the screen. Y is actually pointing down so that it mirrors the screen coordinates if you did a move and draw in BASIC with the origin in the top left. So y gets bigger as it goes down the screen, and z is into the screen. This is a right-handed coordinate system, it's called, because if you take your right hand and tip it so that, let's point that down. So we've got x like this going that way, we've got y down that way, and we've got z pointing that way into the screen. That's our coordinate system. Elite's actually a left-handed coordinate system with y going up the screen, but the same thing. And so you spend yourself time doing this when you're trying to analyze code like this. It's always strange. But basically, the landscape, which is going flat into the screen, is on the x and z plane. So x from left to right, z going into the screen. So this calculation works out the height, i.e. the y coordinate, the altitude of a point x, z on the landscape. And you can see that it takes that value of x and z, pushes it through this Fourier synthesis, adding up sine waves, and that gives the height at that point. So we can calculate the height of any point on the landscape at all just using this process, and that's how the landscape is generated. Let me show you this graphically using some pictures from Wolfram Alpha. Very useful tool when you're analyzing Fourier synthesis like this. So I'm just going to work through, I'll show you the first couple. So sine x minus 2z and sine 4x plus 3z. The first one, x minus 2z, looks like this. And it's a wave going into the screen away from us. And I mean, one way of thinking about this is combinations of waves. So if you imagine, say, a swimming pool, and we've got various people dotted around the edge, 6 people dotted around the edge, in fact, all making splashes and sending waves into the pool. They combine, and that's what the landscape is in lambda. I mean, that's a very simplified model, and it's not quite accurate because actually the waves aren't traveling, and they would need to be slapping the water with a sort of plank rather than a dot so that they're going like they are in that picture. And you don't need sides in this swimming pool because that would reflect. So it's not a great analogy, but if you can just bear with me, imagine someone is sending a wave as shown in that on the screen across the pool, and someone else is sending one across the pool from left to right like that, which happens to be the second element of the landscape synthesis. And if you combine them, it looks like this. And you can kind of see in this picture, there's kind of a wave going into the screen and there's another wave going left to right. And that's just 2 of our sine waves combined. If we combine all 6 and just type that into Wolfram Alpha, we get this picture, which is starting to look a bit like a landscape. Not obviously, this is what we're going to be doing with it. So this is the basis of the lambda landscape. But we do need to add a couple of things before we have the final product. We need to add water and a launch pad. These are reasonably easy. What we do is we define a constant called sea level, and anything below sea level, we just flatten out at sea level. So that brings any altitudes in the sea up to a flat sea. And the same with launch pad altitude. That's the altitude of the launch pad. Anything that's there, we actually build a launch pad at xz, where x goes 0 to 8 and z is 0 to 8. That bit there, we flatten that down to the launch pad altitude. So basically the launch pad is at the origin of the landscape. The front left corner of the launch pad is actually 0, 0. And that's just a bit of code that says if there's a point in this, flatten it down and make it the launch pad. And once we've done those two, we then can redraw it, and you can see that we have a landscape with the flooded valleys. And that, although that's obviously heightened, it's in exaggerated height to make it a bit easier to see, but that is basically the starting point for lambda, and it all comes from that sum of sine waves. If we do a contour view of exactly the same thing, an overhead view, this is what the contour view looks like, so the view from overhead, and if we compare that with the contour map in Zarch. Now, Zarch uses a different algorithm. It's still a sum of signs, but it's different numbers. So it is a different landscape in Zarch to Lambda, but it uses exactly the same process, just subtle differences. But you can see the shapes are broadly similar. This is what you get when you do a Fourier synthesis of 6 sine waves. Yeah, so that's basically how the landscape is synthesized. And now I'll just tell you how it's drawn. Given this, if we look at the landscape, it's actually drawn. Here's a shot from the game. It's drawn as a thin sheet. You can actually see under it on the right of this screen. Because I'm about to crash, you can see that I'm very good at this, but I managed to catch that screenshot just at the right time. And because the right-hand side is sloping kind of up and towards us, we can see underneath. And this kind of gives away a bit as to how the game draws the landscape. I mean, to be honest, you don't really notice this a great deal because you're too busy trying not to die in Lambda. But if you can sort of skim along and see it happen. So how do we draw the landscape, given that we've got this function that gives us the height of the landscape at any coordinate? So the visible landscape in Lambda is 12 tiles across and 10 tiles deep. And actually, if you view the landscape from above, it looks like a chessboard. Every tile is square. It's just that the corners move up and down. But if you look at it from above, it is square. So the way we draw the landscape is we start at the back left corner and work left to right along each row of corners, and then move to the row of corners in front and work along there. And for each of these points, we calculate the altitude of the landscape using the synthesis I've just shown you. And then we project this onto the screen from 3D into 2D. And this uses the same simple perspective projection as almost all 3D games on the BBC Micro, like Elite do, which is just to divide by the Z coordinate, which is the distance into the screen. And that gives us our screen coordinates, a very simple projection to do. So we project them on the screen, and then we store these projected coordinates in a table that I've called the corner store, because that sounded good for storing corners, nice little ring to it. And we work our way along, and once we've got 4 coordinates for a tile, which will happen on the second corner in the second row, we draw each tile on screen. And because we're working from back to front, the landscape overlaps properly. And, so tiles at the back get drawn first and tiles at the front get drawn later. The 3D objects like the trees and so on that sit on the landscape, they also get drawn at the correct point, but I'm going to cover that later. But that's basically how we draw this landscape. There's one other part to the landscape that I'll run through quickly, which is the color of each tile. And this is incredibly important. This is the kind of difference. This is why this is such a beautiful looking game, because the colors used on the landscape are wonderfully convincing. If you imagine doing this with sort of dithered color on a BBC Micro, it probably wouldn't look as good. So let's look at the way that the colors are calculated. And it's basically, we need to take a base color for each tile, and then we need to tweak it with a brightness. So we do this by calculating the slope of the tile, which actually we do with the slope of the front edge. And that's just by taking the altitude of the left-hand point and the altitude of the right-hand point and taking them away. So we get a value of slope, which basically is a positive thing for tiles that point to the left. And it's negative for tiles that point to the right. So that gives us an amount, and it's a higher value, the steeper the gradient of that tile. So we've got the slope value, and now we need to work out a base color for each tile. So the C is quite easy. If a tile is at sea level, it's blue. So that's an easy start. If it's at the launch pad altitude, then it's gray for the launch pad. All the rest are green and brown. And the calculation for this is quite neat. Essentially, we take the altitude of the front right tile corner and we pull out bit 2 and bit 3. Bit 2 feeds into the red hue of this tile, and bit 3 feeds into the green hue. We set the blue hue to 0 because we do not need blue tiles in the middle of the landscape. So the reason this is clever is that if you imagine blinken lights on the front of a computer and you imagine them counting up through binary, you'll know that the bit 0 flashes like crazy as it's counting up, and bit 1 flashes a little bit less fast, and then bit 2 is half the speed again, and bit 3 and 4, and until you get to like bit 8, bit 9, and they're quite slow. And that's that you've all seen that kind of binary thing going up. So red is bit 2. And if you imagine kind of moving up through altitudes, so up a slope, say, or down a slope, the red bit is going to change more rapidly, twice the speed as we go up that slope than the green, which is in bit 3. What this means for the landscape is that we get clumps of reddish tiles together and larger areas of green that change more slowly. So we end up, if you look at that landscape on the screen, you can see there are kind of clumps of muddy bits that are smaller, and they clump together, and there's a much more gentle green vibe. They're much larger areas. So together it does have quite a sort of good feeling of kind of farmed landscape, perhaps. It works very well, and it's just because those two bits are taken one apart from each other in the altitude byte. Very clever. So tile colors, how do we take all this information we've just done and actually come up with the color? Well, the color for each tile is quite simple. It's the base color that we just worked out. And then we set the brightness to the row number plus the slope scaled down. So this means that basically we've already said the launch pad is gray and the sea is blue, and the landscape is predominantly green but with brown patches. Tiles that point to the left have a higher positive slope number, so they are brighter than tiles that point to the right. And the light source in the game is right up there in the sky, but it is slightly to the left. So this fits into that. Steeply sloping left-facing tiles are brighter than gently sloping tiles, which is a kind of a strange, and that sounds like it's the wrong way round, but it works quite well in not making long, large, dark areas of sloping tile. And tiles are brighter towards the front of the landscape than at the back, which makes sense because it sort of peters off as you go into the darkness at the back of your screen. And that's how the landscape is drawn. It's with a really clever bit of Fourier synthesis and some really drawn in a fairly logical way, but using some very clever color routines. And that's the secret of Lander's landscape. Let's now move on to 3D objects, which are in the game are all sorts of things. Well, let's have a look at them, shall we? These are the 13 different object designs in Lander. Starting at the top left, we've got 3 types of tree. There's a tall leafy tree, a small leafy tree, and a fir tree. And below those, you can see what happens to those trees if you shoot them. So you get these 2 destroyed objects, those particles, smoke particles that float through the air. One of it leans to the left and one of it leans to the right. So I've called that a destroyed object that leans to the left and a destroyed object that leans to the right. Why not? In the middle top is our ship that we fly around. And below that is a rocket. The rockets only appear in Lander alongside the launch pad. And below those, the rock is on the left. So the grey rocks that fall from the sky when you get a score of 800 or more. And to the right of that is an unused 3D object, which is a kind of weird rotating pyramid that is never used in the game, but the definition is in there. So that's presumably a bit of a work in progress from Zarch. It kind of looks a little bit like it might have morphed into the radar, the rotating radar at the start of Zarch, but I can't tell from the code. And then we've got 2 buildings on the top right. There's the building and the gazebo. And below them, the destroyed building and the destroyed gazebo. So those are all the objects. And most of these sit on the landscape. The rock falls from the sky, and obviously our ship is in the air, but everything else sits on the landscape. So how are these objects defined in Lander? Now, there's quite a large overlap between the way that 3D objects are defined in Lander compared to the 3D objects in Elite. Not surprisingly, written by the same guy. So this will be vaguely familiar to anybody who's looked at the Elite stuff. So we have a blueprint for each object, which is a hard-coded, read-only description of the object and its shape and some attributes. So the object blueprint contains the number of vertices and faces. It contains a couple of object flags, determines whether an object is static or a rotating object. Static objects are most of the objects like trees, buildings on the ground are static in that they always look the same, don't rotate. Rotating object, the player's ship is a good example because obviously we tilt that as we fly. Also, there's a flag to determine whether an object has a shadow or not. The gazebo, for example, has a shadow, whereas the building does not. If we go back to this, you can see in the top right, you can see the gazebo has a shadow underneath it, whereas the building just doesn't. There's no point in having a shadow under that building because we couldn't see it anyway. So it's got a flag that stops it from trying to draw a shadow. And then the rest of the object blueprints, we've got the data for each vertex, which is each corner in the 3D object, and that's stored as a 3D coordinate in space. And then we have data for each face on the object, and the face is defined by the vertex numbers of each of the 3 vertices that make up that face. They're triangular, the faces, so we can make square ones by putting 2 triangles together, but everything's triangular. Also, we store the face color as an RGB value and the face normal vector. Now, this is the same as in Elite. And a normal vector is, if you've got a face, a normal vector is a vector that points up from the face at a perpendicular, maybe like that, that's better, perpendicularly. And we use that for working out which direction the face is pointing in, so we know whether to hide it and also know how bright it should be. And we'll look at how that's done in a minute. So those are the object blueprints. Because of the way things work, rotating objects, like in Elite, have to be convex and fully closed. And so you'll notice that in fact, the ship is quite an Elite-esque looking ship, and the rock is, like this. So there's no concave stuff because that doesn't work with the particular face hiding algorithm that Elite and Lander both share. Static objects, however, can be open. So the gazebo is a good example. You can see straight through the gazebo, through its legs underneath. And because it's a static object, that's not a problem because we define static objects simply, we make sure that the faces are drawn in the correct order to look good. And they're all, as we're not rotating the gazebo, we know, for example, the front sloping edge of the roof is always going to be visible because it's always going to be pointing towards us. And in fact, there isn't, let's see, can we see if there's a back? I can't remember if there is. Yeah, there isn't actually a back roof at all. You just can't tell. If you look at the gazebo, there is no roof at the back because you can't see it. So the static ones are slightly cheaty, but the rotating ones are kind of full 3D rotating objects like in Elite. And very similar to Elite, but there's no edge data. Elite, of course, is a wireframe, so it also has an extra set of data for each edge in the object because that's what's actually drawn, whereas we're always drawing the face in Lander, so it's a slightly simpler object definition. So we have all these object blueprints, and then we have a bunch of objects, and each of them has an object type. And the object type ties together a particular blueprint with a bunch of other attributes. So there are 24 object types in Lander, and they use 12 of the 13 blueprints that I mentioned at the pyramid is unused. So each type has an associated blueprint, and you can add 12 to the type number to get the destroyed version of that object. So 0 to 11 are the standard objects, and 12 to 22 are the destroyed objects. Some are repeated in terms of blueprint. So objects 1, 3, and 4 are all small leafy trees, and 9, 10, 11 are all rockets. This is, I'll show you why in a minute. This is to control the distribution of objects on the map. Let's talk about the object map. The object map is a big array of 256 by 256 corners that determines where objects sit on the landscape. Now, the landscape's infinite, but the object map is finite, and it actually repeats every 256 tiles. So if you launch and fly forwards from the launch pad, where it has 3 rockets next to launch pads, and you keep going forwards, you'll come across a nice leafy field with 3 rockets in a row, because they're repeated every 256 squares. But because you're too busy fighting and flying and all that stuff, you don't notice it. And 256 squares is a really big area, so it's not a problem. So this keeps the object map being finite. Also, as we have 1 byte for each tile corner, it means we can squish it into fairly small block of memory. At the start of the game places 2048 objects randomly in the object map. It doesn't place them if they're in the sea, so it checks the altitude of the map at that point. It doesn't place stuff in the sea. And because I mentioned that the object types, some of them have repeated, they share blueprints. The chance of each object appearing, we actually only use object types 1 to 8 for objects that go on the object map. So there's a 3 in 8 chance of an object being placed being a small leafy tree, a 2 in 8 chance of it being a tall leafy tree, 1 in 8 chance of it being a fir tree, or a building, or a gazebo. So that explains why there is so much greenery in Lander, because 6 out of 8 of the objects that are placed are trees. And that's kind of what the game looks like, with the odd building or gazebo thrown in there. And the 3 rockets, I said, they go along the edge of the launch pad, but they aren't placed in randomly in the landscape. So that's the object map. Finally, how do we draw these 3D objects? Well, this is not dissimilar to Elite. It's kind of like a souped-up 3D version of Elite. So if we're drawing an object, the first thing we do is we scale up the coordinates, the 3D coordinates, to maintain as much accuracy as possible. And that's just done by shifting the values up into the higher bits in a 32-bit value as far as possible, and storing a scale factor so that when we do things like the calculations, we've got as much accuracy as possible. We then convert each of the vertices from 3D space to a camera relative coordinate. The camera in Lander is actually at the back of the landscape as we're looking at it, rather than it being us, but it's still a fixed point compared to the viewer. So the camera, when we fly around the landscape, the camera moves with us, and that's why the whole thing moves. So when we're drawing what's on screen, we convert everything to a camera relative position, because by definition, that is what a screen shows, camera relative content. If it's a rotating object, we apply a rotation matrix to it, which I'll talk about later, and that just rotates the object in the right way. So our ship has a rotation matrix associated with it, depending on how we're steering it in space. Just like Elite, the rotation matrix is made up of orientation vectors. It can be thought of as 3 vectors. We've got the nose vector. Where are we? Well, that's this side, isn't it? So we've got a nose vector, a roof vector, and a side vector. I'll talk about these more in a minute, but it's the same kind of system as in Elite, just slightly tweaked, and it's actually turned upside down because it's a right-handed coordinate system, as I mentioned earlier. So for rotated objects, we calculate the visibility of each face on the object by taking the face normal, which is in the blueprint, and doing a dot product with the angle towards the camera, so that we know whether the face is pointing away from us or towards us. And then we do draw it or don't draw it, basically. Static objects, don't bother with this. We know that every face in a static object is drawn so that it looks correct. Then the next thing we do before drawing the face is we draw the face's shadow, which I'll explain in a minute how that is done, because that's a really key part of why Lander looks so realistic, the shadows that go on the landscape. So we draw the shadow first, because obviously a shadow is always never on top of the face that is casting it, otherwise that would make no sense. We draw each face and we draw it in a brightness that is proportional to the y coordinate of the rotated face normal. So if you imagine the face is pointing like this, how much is this face pointing towards the light source that's up there, which is the y coordinate? That's the y-axis, which is actually going down there, but you can still think of it like that. So we basically take the y-axis of the rotated normal, and that it determines the brightness, because it determines how face on to the lighting source up there in the sky that face is. And we also add a little bit of the x coordinate because the light source is slightly to the left up in the sky, so that's consistent with the rest of the game. Have a quick chat about shadows before we move on to particle clouds after that. You can see in the game here, there's a couple of screenshots. The shadows are really important. The shadow of things on the ground have shadows like gazebos, but the shadow of the ship cast down onto the landscape is a really key part of why this feels like a solid 3D environment. And as rocks start to fall from the sky, if you manage to reach 800 or more, you can see the shadows small, grow, and it's a really clever piece of, you can see them coming before they hit you, so you can get out of the way. So that's a really important. It's much more important in Zarch, of course, because there's ships everywhere trying to kill you and flying around, so you can spot them by their shadows before it all goes wrong. But Lander has the shadow system, and shadows are just shows you where they're drawn in the 3D object routine. But basically, we take the face and we just project it down onto the landscape, and that's the shadow. It doesn't drape properly over the landscape, but you would never know. It's actually each shadow is like a plate with 4 corners, or 3 if it's a triangular face. So it is flat. It doesn't drape over the corners of the landscape, but it doesn't matter because things are going so fast, it's completely convincing. So it's very quick to do, because all we have to do is drop down the vertices of each face down onto the altitude directly below that vertex, which is quite a quick calculation. So we drop the face down onto the landscape, we project those onto the screen, and then we draw the shadow in black using those vertices. And we make sure we draw the shadow before the face that casts that shadow by using the depth sorting, which I'll talk about in a moment. So there's another clever little bit here, is that this is a part of the way that Lander detects whether you've crashed into the ground. If the shadow of the lander has a higher altitude than the lander, then the lander has crashed. So that's a quick check to see whether we've hit the ground. Much more efficient than trying to work out whether the thing has, crossed across this landscape that we've got. So that's quite a neat little trick. Another really impressive part of Lander is the particle system and these particle clouds that explode and splash and do all sorts of things. These are the types of particle. From the top left is showing bullets that come out of the nose of our ship. They're all particles. Middle top is exhaust. The exhaust plume fires out of the bottom of our ship. On the top right, we've got smoke and debris particles. You can see a smoke cloud rising up from, a crashed ship on the launch pad, of course, you can tell. And then underneath that are a bunch of debris particles bouncing around on the launch pad. Bottom left is a bunch of spark particles in an explosion. Bottom middle is spray, which is when things collide with the sea. And bottom right is the rock. Now, the rock is a 3D object, not a particle, but it's modeled as a particle, so that it falls down just as a particle would. So Braben built this particle simulation system that basically simulates all of these particles and applies physics to them, and they bounce around and they do exactly what you would think. So you have smoke rising and particles bouncing and exploding and so on. So I'm going to explain how this works. The core data structure behind this is the particle data buffer. This contains up to 484 on-screen particles, the data for each of them. And the data it stores for each of these 484, up to 484 particles. First of all, we have the XYZ coordinate in the 3D world, so exactly where the particle is. We have a 3D velocity vector, which is how the particle is traveling in space. We have a lifespan counter, which ticks down every iteration of the main loop by 1. So if you have a lifespan counter of 10 for your particle, it will last for 10 main loops. And then there's a set of particle flags that determine the particle behavior. Let's have a look at the flags then. So the particle flags define the particle color. They define whether the particle fades from white to red over its lifespan, which is used by the spark particle, going from white hot to red over time. There's a flag that determines whether the particle is a ROCC, because the ROCC is a special type of particle that drops in the sky when the score reaches 800. Does our particle create a splash on impact with the sea, or does it just disappear into the sea? And if it does, is it a big splash or a small splash? Those are all flags. Does it bounce on hitting the ground, the particle, or does it just stop and disappear? Or does it explode on hitting the ground and generate more particles? Do we apply gravity to the particle, and can the particle destroy objects on impact? So to take a couple of particles, the bullet, for example, it splashes on the impact with the sea and gives a big splash. It explodes on hitting the ground. We do apply gravity to the bullets, and it can destroy other objects if it hits it. Whereas a spark particle splashes on impact with the sea, but with a small splash this time. It also bounces on hitting the ground. We apply gravity to the particle, and the color fades from white to red over time, from white hot to sort of dull red. So each of the particle types has its own collection of flags that define how our particle behaves. So how do we model all of these particles? Well, we basically, every iteration around the main loop, we move and age these particles according to the particle flags and update the data in the particle data buffer for every single one of these particles that currently exist. So the steps are fairly logical. First of all, we age the particle by subtracting 1 from its lifespan, and if that reaches 0, that particle has expired, and we get rid of it and delete it from the buffer. We add the velocity vector to the particle's coordinates so that it moves in space by the correct velocity. We add gravity, so that's another velocity vector that points down towards the ground. If it's configured to fade the color from white to red, that's what we do, a little bit every time. And we also, if it's configured to destroy objects, we do some collision detection to see if that particle's 3D coordinates are within the space taken up by the object. We process collisions with the ground and the sea by checking the altitude of the point directly below the particle and see if it's the same as the particle altitude. And if so, then we apply the flags to determine whether it bounces or whether it explodes and so on. And once we've done all this, we then update the particle data buffer for that particle and move on to the next particle and do all this again for that one. So this is a big loop that we go through. It's very fast. I mean, the Archimedes is a nippy machine, so it can process quite a lot of stuff quite quickly like this. So another part of the particle engine is that when we spawn a particle, there are random factors depending on the type of particle. So there's an initial state that gets set up, and that can be quite random. So for example, smoke particles are given an upwards velocity of 80,000 hex, and which means that they rise up slowly like this, whereas exhaust particles that come out of the engine at the base of our ship are given a much faster velocity of 400,000 hex along the roof vector, which is the vector that points out of the bottom of the ship and which gets rotated with the ship, so that the exhaust always shoots out of the bottom of the ship. So that's defined in that type of particle. But also, for certain particles, we can add a random factor to the initial configuration. So when you're creating an explosion, for example, you create spark particles, but you give them a really big random velocity factor. So some move slowly and some move quickly, which, you know, if you think about how an explosion works, that's basically what you want, because if you gave them all the same velocity, it would be a shell that isn't really what you want. So you want some to go slow and some to go fast. And smoke particles, meanwhile, are given a big random lifespan factor. So your cloud will dissipate slowly over time, rather than all of them, you know, winking out of existence at the same time. some will die quickly, and some will live for quite a long time, which is, looks pretty realistic for a smoke cloud. And explosions, such as when you destroy an object or hit the ground, are a combination of short-lived sparks and long-lived debris and smoke particles. So if we have a look at an explosion, on the left is the early stage of the explosion, and this is where the short-lived sparks predominate because they're, heading from white through to red, so they're in quite a yellowish state in there. At the point I took that screenshot, there are actually debris and smoke particles in there, but they're quite hard to see. The smoke cloud is a tiny little sort of glob in the middle, and the debris particles are just a bit different. They're along the bottom, really. You can't see them, but the sparks are short-lived, so they disappear quite quickly while the smoke cloud slowly rises up. And you can see on the right is what it is like soon after, when the sparks have almost all dissipated. You can see the debris bouncing on the ground underneath, and the smoke cloud gently rising up as you think, well, that's another life gone. And that's the cloud, the particle cloud system. It's a very clever, finite, simulation system. Very neat. Now, I've talked about or mentioned depth sorting of objects a little bit, and how we, with the landscape, we started drawing the landscape at the back and then drew it forwards, which makes sense. You can kind of understand why you would do that. We have to do the same with objects to make sure that they overlap in the correct way. And the problem with this is normally you sort them. Depth sorting is a known thing in 3D graphics, but sorting is a very, very slow process. And if you're on a machine that's, this is back in 1987, and sorting lots of objects and lots of faces and lots of particles is a slow process. So Lambda doesn't do that. It doesn't bother with the sorting because that would be too slow. So instead of sorting our objects into order, as we draw them, we drop each of them into a bin, a buffer. It's called bin sorting. Basically, what we do is we define 12 buffers. We define a buffer for the rear part of the landscape, right at the back, the back tiles. We then define another buffer, that's buffer 0 at the back, and then the one in front of that is buffer 1, and the one in front of that is buffer 2. So when we're drawing an object, we look at where it is in terms of the Z coordinate, how far into the screen it is, and which buffer is it above, and then we draw that object into that buffer. And then when we're drawing the screen, we draw the buffers. We draw everything in buffer 0, and then everything in buffer 1, and then everything in buffer 2. So there's no sorting required anywhere in this process, but we get the effect of sorting just without the slow sorting algorithm. It's very neat. It's called bin sorting, and it's a very clever little approach. We also just make sure that the shadows for each of these objects and particles are drawn in the buffer before. So we put them into buffer n and put the actual object into buffer n+1 to ensure that the shadow is always behind the object. Otherwise, it would look ridiculous. So we can use the buffer to ensure that things look correct in terms of shadows as well. The graphics buffers themselves are data structures that we encode the object as we put it in there. So each buffer only contains triangles or particles. That's what it contains. Each object is made up of filled triangles, and then you have the particles, which are basically dots of a certain size. So when we're drawing into one of these buffers, we draw either a triangle or a particle, a set of triangles and a clump of particles. So this data is encoded in each graphics buffer as a command block. The first byte of each instruction, if you like, or a triangle or a particle, is the first byte is the command number, which is 0 to 19. So 0 to 8 are particles, going from big particles to small particles, and 9 to 17 are the equivalent shadows for those particles, which are slightly smaller than the particles themselves and in black. And command 18 is a triangle, and command 19 is a terminator that we basically bung on the end of each buffer when we've finished drawing, so that then when we actually come to draw what's in the buffers, we know when to stop. And these are encoded very simply as the first word is the command number, and then it's either one data word or 7 data words. It's one data word if it's a particle, 7 data words if it's a triangle. And the particles encode into the one word, the 32-bit word. They encode the XY screen coordinate of that particle and the color of the particle. And it's the command number determines the size of the particle that gets drawn. Whereas triangles have 7 words of data, which is 2 words for each of the 3 vertices in the triangle, and a color byte as well, which takes up 32 bits. So we use black for shadows, and that's it really. That's how the graphics buffers work. And then we draw them, and we draw them at the same time as the landscape. As we're working through the landscape from the back to front, we interleave the object buffers, the graphics buffers as well, so that they sit at the right point in the drawing process. So specifically, when we draw graphics buffer, n is drawn after tile row n+2. Is that right? That might be wrong, actually. I think it might be graphics buffer n+2 is drawn after tile row n. No, hang on. Anyway, I think I might have got myself confused there. But basically, there's a gap of 2 between the tile at the back and the graphics buffer. Yes. Anyway, skipping ahead, it just ensures that the objects are always drawn in front of the tiles that are under them by 2 tiles worth. And that works well, and we don't get overlapping objects and underneath the landscape. Objects on the same row are obviously drawn at the same time. We just work through the graphics buffer and draw the whole lot. But because they're spaced out across the line, we don't really, it's not a problem with them overlapping because they're always spaced out enough. And the shadows, as I said, are always drawn first as they're one buffer behind the corresponding object, so that they never overlap the object that's casting the shadow. Right, let's talk about flying by mouse. Oh, this is a difficult subject. And if you've ever tried Lander, you'll know that you almost certainly died straight away. I did, I still do. It's ridiculous. But once you get airborne, there is a method to the way this works, and it helps to understand what's going on. So, of course, this being David Braben, it's very mathematical. And Lander and Zarch use the same approach, and they use polar coordinates. So let me explain how this works. Right, so when the game first starts up and starts a new game, wherever the mouse is determined as the center point, okay? And I've marked that in the center of this mouse mat. It could actually be anywhere, but let's just assume it's in the center of the mouse mat. So that's where you are when the game starts. You'll notice this is a B-Bug mouse mat, which is what I had when I had my Archimedes Go B-Bug. So you can insert your own logo there in your mind, but I'm sticking with the B-Bug mouse mat. So let's see what happens. We move the mouse away from the center point, and the way it works is that the direction in which you move determines the direction that your ship is pointing in, and the distance that you move determines the pitch of the ship. It's really hard to get your head around that without trying it, and it's a pretty difficult thing. But how is this converted into a ship position in space in the code? Well, given we've got our center point there and we've moved our mouse up top right there, so what we do is we obviously take the X and the Y coordinates, which we get from a call to the Archimedes operating system, and fetch those, and we use those to convert those XY Cartesian coordinates into this polar coordinate. A polar coordinate is a way of describing a coordinate using an angle and a distance. So the distance is the distance from the center point, the origin, to our point where our mouse is, and the angle is the angle with, in this case, with the sort of Cartesian x-axis. So we convert that, and we do that using some pretty simple maths. The distance, we just use Pythagoras' theorem to calculate the length of the distance of that triangle, which is square root of x squared plus y squared. And we get the angle using arctangent. Tangent is opposite over adjacent in terms of triangles. And if you look at the triangle, the opposite is y and the adjacent is x. So if we then arctan y over x, we get our polar angle. So that's how we convert from Cartesian to polar. And that distance that we've calculated determines the pitch angle of the ship, because that's how far we've moved our mouse away from the center point. And the polar angle determines the direction that the ship is pointing in. So we can update our ship. We actually store the ship's position as pitch and direction angles. And we update the ship by basically not just by replacing the pitch and direction with the new values, but by damping those in. So those are the equations there. So it's not an instant change. There's a slight inertia to it, which makes it a lot easier to fly. If you take that inertia out, it's carnage and really, really sensitive and very difficult to fly. With the damping, it's a lot more natural, because if you think about flying a plane, you kind of turn, well, I don't know, I've never flown a plane, but I assume that if you turn stuff, it doesn't immediately turn around, but slowly kind of moves around. So it's mimicking the real world a little bit more, and it does help. So this pitch and direction angles, we then convert into a rotation matrix. Now, I'm not going to go into what rotation matrices are, but essentially a rotation matrix is a way of describing the orientation of our ship in space. So if we've got A is our ship pitch angle and B is the ship direction angle that we calculated before, we can create this rotation matrix, and that defines the ship's direction in space. The underlying maths is quite simple trigonometry, but because we're combining a pitch and a direction, it gets a bit more complex. But that looks very similar to the equivalent in Elite. So this is a very similar process. It's actually a different rotation matrix because we're dealing with pitch and direction rather than roll and pitch in Elite. But underlying this, another way of looking at a rotation matrix is as these three orientation vectors. So I mentioned it before. We have, you've got the nose vector coming out of the front of our ship. You've got a side vector coming out of the side of the ship, and you've got a roof vector heading out of the roof. Although actually, because it's this way round, and I was using the wrong hand there, this happens to me all the time. Actually, the roof vector points out of the base of the ship, out of the bottom, so where the thrust goes. But it's the same concept as all the ships in Elite use the same orientation vector or rotation matrix, depends what you want to call it. They're the same thing, uses the same approach. So we can use these orientation vectors to apply thrust and bullets. So if we're flying our ship along, you've seen that the exhaust comes out of the base of the ship. So this is along the roof vector. So the thrust vector is actually in the opposite direction to that. So it's the opposite direction to the roof vector is where the thrust is, but the exhaust plume heads out along the roof vector. So we can move the ship by simply applying a thrust vector to the ship velocity in the direction of roof V, and the size of that vector that we apply, it depends on whether you're flying with full power, which is the right button, or the hover mode, which is the middle button, which is one of the features that Zarch doesn't have. The exhaust plume as well, as mentioned there, that heads out on roof V out of the bottom of the ship. So when we spawn our exhaust particles, we give them an initial velocity of the ship velocity plus the roof vector, or a factor of the roof vector, so that it heads out, if the ship's moving, and so it kind of goes like that out of the bottom. So, as you would expect it to do. So it's quite easy to do once we've got this rotation matrix to add these things. Same with bullets. Bullets fly out of the nose of the ship, and we have a nose vector in the orientation vector there, and it shoots out of the nose. So we spawn bullet particles with the velocity of a ship velocity plus the nose vector, or multiple thereof. So that's how that all works, and it all comes from this polar coordinate calculation that we are supposed to be flying our ship with, or not, as the case may be. Not much left, so that's all the heavy stuff. I'm briefly going to mention some of the aspects of Lander that are a consequence of the fact that it was built on an ARM1, on an ARM evaluation system hooked up to a BBC. So it started in 1986, as I said, on this ARM evaluation system, and only moved to the ARM2 when Braben was lent the A500 prototype, and that's the quote he had. about the A500. It didn't even have a disk drive. That's how basic it was. So it was pretty tricky stuff. But code-wise, the ARM1, or the ARM as it was just known then, does not have the multiply instructions, mul or MLA. So he couldn't do any multiplication in the code or using the ARM instruction. So he had to roll his own multiplication routines. These use the shift and add algorithm that Elite uses, very much the same approach. I suspect that they're inserted via a macro or a def function definition, defn in BASIC. I don't know because I haven't seen the code, but they're dotted throughout and they're inlined, and you would probably do it like that. As a result, there are no multiple instructions, multiply instructions in Lambda or in Zarch, because presumably by the time he got to Zarch, he'd already written all the difficult stuff and didn't need to sort of do the hard maths. It was mainly gameplay stuff by that point. So no multiplication instructions. There's also no ADR directive, which is an address directive, which it's not actually an ARM instruction, but it's an assembler directive that allows you to put an address into a register, and it actually does that by adding an offset to the program counter. So there aren't any of those in there. No reason why not. It was actually supported in the ARM evaluation system, but instead he uses vectors to store the address. So you store the address that you want to load in a location, and then you just load the contents of that location into your register instead. So it's just a stylistic thing, but it's an interesting one that feels very BBC Micro rather than RISC OS. He also doesn't use the SBC or RBC instructions. It does use the sub, no RBC, but he does use sub and RSB. So there is subtraction, obviously, but he never uses the carry, which is interesting because it got 32 bits. Coming from the 8-bit world, it was all about carrying over multi-byte, carries when doing multi-byte calculations. But on the ARM in Lambda, it all fits into 32 bits. You must have felt like it was Christmas in comparison. So that's an indication. In fact, the whole game uses just 21 different instructions, obviously far more than 21 instructions in the game, but the variety is only 21. So it really is a RISC game. It's a RISC, it's more RISC than the ARM one. That's quite interesting. And also, I think really that this is the only game ever written for the ARM one. I don't know of any other examples, because by the time it came out, everybody was on the ARM 2, of course. He was the only one who was given access to the prototype to do this and write something for launch. So you can definitely see the ARM 1 influences in Lambda and Zarch, though a lot of these carry on into Zarch, which is interesting. A final part of my talk is a quick mention of Big Lambda. You've seen a picture of Big Lambda before. There's a great article in the Micro User magazine from November 1987, in which David Braben talks about Lambda. He basically explains a lot of the stuff that I've been talking about tonight. And he, one of the things he talks about is how Zarch may have looked. The caption there is how Zarch might have looked, a display technique that was rejected. And you can see it's got a really big landscape. It's actually got a bit of blue in the landscape as well, which is interesting because the code to set that is still in Lambda. It's just ignored, but it doesn't that value doesn't get used. We always set the value of the blue channel for landscape to 0, but that code is still in there. It looks great, but as he says in that article, with the display technique chosen, the frame rate dictated the approximate number of tiles which could be used and also the amount of scenery. The display looks much better if these are greatly increased, as the picture on this page shows, but sadly this reduces the frame rate to only 1 or 2 frames per second, a succession of stills. So although he built a version of Zarch that looks great, it would not run acceptably on an ARM 2. But of course, these days, we've got RISC OS running on modern processors, and of course, the original Archimedes went through lots of increasingly impressive processors as well. So we don't have that problem. So if we could increase the size of the landscape, would it look good? And the answer is yes. I mean, I've shown you this one before. This is a 64 by 64 tiles, which I chose to try to get as close as possible to that mythical picture in the micro user. It's not bad, you know, it's got some vaguely similar kind of feel to it. There's not so much blue, but so we can do this. And this version, the 64 by 64, runs pretty well on a RISC PC with a strong arm. It's very playable. It's quite difficult because I mean, it's not so bad in Lander. There was a project on Stardock to do the same with Zarch, and that makes it very hard to play because you can only sort of fight with ships that are close to you. There's less fighting in the air. There's no fighting in the air in Lander. There's only dodging rocks. So it's actually a lot easier to get your head around the large landscape in Lander. But it doesn't matter because it just looks so lush and beautiful. It's a pleasure to fly around, really. And the bullets do work. You know, if they disappear into the distance, you can destroy stuff that's quite a long way away. You're not restricted to the 12 by 10 original thing. You really are playing in this landscape. It's charming. And for those running RISC OS on a Raspberry Pi, a bit more grunt in the CPU, you can bung it up to about, I think 121 squared is the largest that has any meaningful. If you go beyond that, it starts to wrap around and break. So this is about as big as it gets. And this is really playable on a Raspberry Pi. It's great. I mean, it was very easy to do. I'll just explain how I did it. As I was going through the code and analyzing it, I basically made a note of everything that was remotely related to tile size and tile counts, and extracted those into constants with capital letters as the names. So things like landscape Z front, which is the Z coordinate of the front of the landscape. You've got the camera player Z, which is the camera location, the Z coordinate of the camera location, how far into the screen it is. And landscape X half is a count of how many tiles there are from the left-hand edge of the landscape to halfway along the landscape, going from left to right. So these are all calculated. They're fixed constants in the code, and so I pulled them out as build variables, if you like. So they're still constants in the code, but it meant I could change them in one place and see what happened. And it turns out that all of these values could be calculated from just two values. The count of tiles from left to right, which is 12 in the default game, and the count of tiles into the screen, which is 10 in the default game. So I named those tile X and tile Z, and made sure that all the buffers that store things like the object map and the corner stores and all those things used the values of tile X and Z to size them accordingly. I had to hack the tile color routine to cope with arbitrary depths, because otherwise it would go white beyond the back, or black beyond the back, white beyond the front. It was all a bit wrong. So basically, Big Lander only changes the brightness in the first 10 tiles, and then it's all the same in the back, which is not bad. It could be better. Zarch does a much better job of that, but I've got to leave some cool stuff for Zarch to do better than Lander. And I also had to fix a couple of issues. As I mentioned before, Lander doesn't work on RISC PC, and the reason is that it has hard-coded screen addresses in the source, which is fine for RISC OS 2 and 3 and Arthur, but no good for the RISC PC. So instead, it's replaced with a SWI call to read VDU variables to get the screen addresses and use those instead. And there's also a memory detection routine in Lander that checks to see if there's enough free memory on the A305 by writing to location 0, which is a pretty disastrous thing to do in a RISC PC, and just hangs it. So that just disabled that and switched it off. And then suddenly, and in fact, to be honest, these fixes were from the Stardock community, so I can't take credit for inventing them. Plugged them in, lo and behold, Lander running beautifully on all versions of RISC OS up to the modern day. The final step was to enable you to pass the tile size as a build variable. So the Big Lander repository that's on GitHub, you can build an arbitrary, choose your size, build it. There you go, Lander running at your own custom size. So you can find the perfect tile size for your own configuration so that it runs at just the right speed. Right, well, that's pretty much me done. The last thing to say is that this is all online. The address for the Lander website is lander.bbcelite.com. Everything in this talk is on there. The source code is linked to from there. There's details on how to build it. There's deep dives. There's the actual source itself. And then there's the same deal for Elite, Aviator, and Revs at those URLs. So if you're into getting stuck into some David Braben code, that will keep you going for some time. And that brings me to the end of my talk. So thank you very much.
Any more Mark questions? Unmute yourself and ask away.
I think you've stunned everybody.
This happened with Elite as well. Information.
I just saw the maths and that was it. At school, I often wondered what the dickens we were going to use these things called sines and cosines and goodness knows whatever for in real life. Now I know.
Yeah, 3D graphics is trigonometry, definitely. I mean, people ask me how do you analyze this stuff? And to be honest, after a while, when you're analyzing a 3D graphics game, you know there are going to be these same things in there somewhere. There's always going to be a dot product somewhere in there working out whether, you know, faces on an object are visible or not. Somewhere in there's going to be some kind of gravity. You know, these things are quite common. So it's, but I mean, particularly in this case, because the author's the same as Elite's. Yes, very familiar, some of it, but yeah.
One or two comments and questions on the comments section.
So there's a question in there from Nitrex. Have you become a better coder from delving into all these game codes? Definitely. In terms of 6502 assembler and ARM assembler, oh yes. I mean, I learned them both when I was a teenager. I didn't really write any 6502 assembler because I was kind of, I don't know, 13, 14. I didn't have anything to write. I mean, the best way to learn these things is either to have a project to do or to have something to analyze. But I did learn ARM assembler when I got my Archimedes, and I wrote 3D graphics programs back then. I wrote one that was an icosahedron of jelly inside a cube, and you can rotate the cube and the jelly bounces off the inside of the cube and all wobbles just like proper physics stuff. I wrote that while I was at university, and that was all in ARM code, and it was completely an homage to Elite. You know, this stuff blew my mind and I loved it, and I really wanted to know how 3D graphics worked. So yeah, definitely I was doing ARM for a while, but I hadn't done ARM for a long time. I did that back then, and hadn't touched it until I started looking through Lander, and I must say it brought it all back, and it's a delight. I love ARM code. It's so especially having, you know, been analyzing really compact 6502 code with all of the kind of shortcuts and, you know, hacks and things like that. You suddenly find with ARM code there's all these registers and conditional execution. You don't have to jump around all the time, and you know, you can move blocks of registers from here to there, and it's really simple. It's an absolute delight. I must say, really enjoyed it. So I'm going to have to look at a bit more ARM code, I think, probably. But yes, it's definitely made me a better coder with Elite. Particularly, I've done a lot of hacks on Elite, and, you know, making it flicker free and teletext delete and various other things like that. And you have to sort of be able to cope with that level of code in order to do it. But yeah, definitely. What else have we got? Lander was also bundled with the A5000 learning curve. Oh, was it? I didn't know that. Okay, so it wasn't on the app discs for RISC OS 3, I don't think, was it? But it came with the learning curve. Oh, brilliant. Well, that's great. Good. They hadn't forgotten Lander after all. That's nice. Nice to see it going in an educational package there. Perhaps it was trying to teach them physics and the effect of gravity on planes. But okay, that's great. Am I planning to deep dive any more games? Yes, but I'm taking a bit of a break at the moment because I've just finished. The last project I finished was a for a deadline. So I volunteer at the National Museum of Computing in Bletchley Park, and a couple of weekends ago we had an Ethernet LAN party where everybody brought their machines, hooked them all up in the Ethernet network, where they've got a wonderful classroom full of networked beebs and arcs there, and everybody bought their own. We hooked them all together and created a huge Ethernet network with people joining from abroad using the Pi Ethernet bridge system. So that was great fun. And for that, I extended Elite in a couple of ways. First of all, so that it could load over Ethernet, because Ethernet grabs a whole chunk of memory for its own use that clashes with Elite. So I rejigged Elite so that it could be loaded and run properly over the Ethernet network. And I also added some code to support multiplayer scoreboards, so that you have one machine on the network running a scoreboard in mode 7, and all the Elite instances on the network on the various machines, you can point them at that scoreboard server with a configuration screen, and it sends your score, so your kill rate, your credit levels, your legal status, all that stuff. It sends it, just pings it every now and then to this scoreboard, and the scoreboard shows the scores in order, so you can have competitions. And we had a scoreboard with about, I think it was 11 real human beings. There was some test accounts in there as well, but we had someone dialing in from North America playing Elite. We had someone in Switzerland, and we had a bunch of people around the UK, as well as the people on site, all playing Elite at the same time. I mean, it's not true multiplayer Elite, playing against each other in terms of actually, fighting each other, but they were competing. So it's multiplayer like golf rather than multiplayer like tennis, but it's still multiplayer. So that was, anyway, I was burning the midnight oil to get that ready for the party. So right now I'm having a bit of a breather. But in terms of next projects, well, ones that are appealing, I would love to go back and do some more Jeff Crammond analysis, having done Aviator and Revs. So I think the Sentinel has to be on the list somewhere, because that's an epic BBC Micro game. Also Exile, which is an absolute classic BBC game, and the code inside it is supposed to be absolutely stunning and mind-blowing and really hard to understand. So that sounds like a challenge. I'm also quite interested in Stunt Car Racer, it's a Commodore 64 game, but it has been backported to the BBC by the Bit Shifters. So that's worth checking out, because it's another Crammond game, and he's just honestly, Jeff Crammond's up there with Bell and Braben in terms of his incredibly clever code. We're very lucky on the BBC Micro and in the Acorn world to have such high-powered, genuinely impressive geniuses pumping out these games. So I think it's quite hard to resist wanting to poke around and see how they did it. So there's a few on the list there, but I also have a habit of getting distracted by by other things, because these projects take months of quite a lot of effort. So I'm gearing up for that. And to be honest, it's summer out there at the moment, so I'm doing things like the garden and the DIY that need doing. And when the nights draw in, I'm sure it'll be hard to resist looking at the next game.
Yes, fascinating.
Looks like it was popular in the school as well.
Well, I got Lander on. I had the A5000, I think. That was my first ARM machine, and that definitely came with Lander. So I must have got the educational stuff chucked in.
Yeah, well, that's really
Never
good.
could fly it.
No, nobody could. I mean, I bought Zarch. When I bought my Archimedes, I ordered Zarch with it, and loved it. But I couldn't play that either. I mean, it's actually more difficult because you take off and people try and kill you. At least with Lander, there's you're the only way you can really die, I mean, unless you're good enough to reach 800 and get the rocks falling from the sky. But the only way you can die in Lander is by hitting something and actually colliding. Whereas in Zarch, they're literally gunning for you. So it's really hard. So I bought the game, looked at it for a bit and thought that's lovely, but I just never got anywhere. And I mean, there are people. It's one of those things. I mean, it's difficult as well because these days, I use a trackball, and you try playing Lander with a trackball, that's a whole other world of confusion right there. But it's still a great game. I mean, you fire it up and just look at it and think that's wonderful, and it's a pleasure. And Arch does have a demo mode as well, which is probably it's probably the most therapeutic way to play Arch, is watch it play itself.
One or two more comments come.
Could Lander be updated in the same way that you updated Elite? Well, teletext Lander. Oof, that would be, it might be a bit tricky. Well, I mean, it could be. I suppose, transmitting score to an Ethernet-based, scoreboard, as with Ethernet Elite, would be fairly easy, because that's just bolting in a few calls to the operating system to send a data packet over the network. And so that would be relatively straightforward. I mean, a teletext version is slightly trickier on the Archimedes, because, of course, it has mode 7, but it's an emulated mode 7. It's not a real one. So it wouldn't look exactly the same. And I think maybe, it's filled stuff as well, and filling things in teletext with color is incredibly difficult. Elite worked quite well in teletext because it's black and white, but teletext, you have to devote a whole character to changing the color as you work along each row, and so multicolored graphics is just not really feasible in terms of moving graphics like this. You have to be, if you're drawing multicolored teletext graphics, you'll notice there's lots of sort of black edges, and that's because that's where the color code lives. So I suspect that Lander in teletext would be a step too far, because I just don't think it would work in monochrome. Bit of a challenge, but yeah, it's a great idea though. What have we got here then? So this is sounds like a simple question, but it's a very valid one. But having always died near instantly in Lander, is the aim of the game to shoot trees, buildings? How do you get points? The main thing lacking from the game was instructions. Well, quite right too. The aim of the game is to destroy anything. You lose a point for each bullet that you fire, and then you gain points for each thing you destroy. So destroy anything, and so it's trees, buildings, rockets. Then you get points. So it is just a destruction game. So not deeply thrilling, and not very deep either, and all a bit of a shame really on such a beautiful landscape. But yes, the idea is just to kill everything. There were instructions in the applications guide that came with Arthur and RISC OS. They were really short and not really very friendly. And in fact, the advice for how to fly Lander in the manual is to turn your mouse. And if there's one thing you don't really do, it's turning a mouse. I mean, you move a mouse, right? If you turn a mouse, nothing happens, except you get very confused about where to move it. So the instructions are pretty rubbish, to be honest, which may have didn't really help us back in the day. But yeah, it's just to destroy things. So obviously Zarch has a much more sophisticated model in that, your job there is, and it's still just to destroy things, but it's things that are destroying the landscape. And, there's a lot more skill in fighting another ship in 3D space than Lander, where it's just killing things that are on the ground. But yeah, essentially it's destroying things in both games is how you get points. Could more objects be added, or is the number 2 hard coded? No, the number's not hard coded. So yeah, you could add more objects. It would also be relatively straightforward to, for example, I thought about doing this but never got around to it, to change the ship that we fly to one of the ones from Elite, just to see what it may have looked like if this had been used in Elite 2. But of course the thrust comes out of the bottom of the ship, so the only real ship that works for is the Thargoid mothership. So that sounded quite a good idea. Thargoid mothership going around destroying things on the ground. That sounds like quite an entertaining thing to do. But no, you could add more objects. There's not much hard coding in Lander, at least not in the version now that's been documented, because all those things have been pulled out as variables. So you could change them relatively easily, especially if you're not trying to fit it into an A305. Once you get past that, you can expand it in lots of ways. So yeah, that could be done. Did I dabble with the color code to introduce blue into the routine? Well, I did switch on the instruction that's in there that adds, it sets a blue channel value in a variable, but it doesn't actually then integrate that into the VidC color that is sent through. And I did turn it on, and the landscape did look a bit like in that micro user picture, but it looked awful, really. The beauty of the kind of the green and brown muddy fields in the green fields, it all went a bit weird, and looked a bit like the colors had gone wrong on the Archimedes. So it looked like a bug, frankly, when you're used to the landscape as it looks in the finished game. But so I did dabble with it, and then I undabbled it pretty quickly after realizing that wasn't really going to help. And it's interesting that it did sort of match the experimental picture from the micro user there. Another question here is, given that you mentioned there's an unused object in the Lambda code, what about turning it into an in-game object to add something more to it? Well, yeah, I mean, that definitely, in fact, it's quite easy to use that triangle, because when you're creating objects in Lambda, putting them on the landscape or dropping rocks from the sky, each of these has a blueprint number, so you can just change the code to use the pyramid, which is how I found out that that's what it was. Just change. Actually, the easiest thing is to change the rockets along the edge of the launch pad, because then all you need to do is start the game and you can see all the different objects. That's how I found out what they were, by hacking that code to change the ID. So it's trivial to put that into the game, but I mean, if you're adding it to do something more, then I guess it depends on what, because to be honest, the objects in Lambda don't do a great deal. Most of them are static and just sit on the landscape, and they just sit there until you destroy them, and that's the end of that. You've got the rocks that fall from the sky, and then you've got the ship, your own ship, but that's it. So introducing new objects, it's relatively easy to introduce objects that also sit on the landscape. They wouldn't do a lot. But if you wanted to add anything like enemy ships, you would have to build, AI around those ships and tactic routines and all that, which obviously has already been done in Zarch. So Zarch is probably a better game to start hacking new objects into, because you could add, tweaked tactics to them and so on. Haven't analyzed Zarch. I'm not really planning to, because one of the good things about Lambda is everybody's got it. There's no commercial value. It was given away free. It is a copyright game, though, as it says along the top. So I'm very keen to respect and not have any financial implications of the projects I'm doing. And it's free, it's out there. So me pulling it apart and adding extra tiles and stuff is hopefully not going to offend anyone. Whereas Zarch is a game that is the copyright is owned by the author, and Superior Software still exists as a going concern. So that is a more commercial thing in there. So I won't be pulling Zarch apart. It's also the same reason why, the amazing work done on Stardot to expand the Zarch landscape hasn't been released in any way. So, but that would be the one to hack around if you wanted to add, objects and crazy tactics and so on. But yeah, definitely a different level of project that. Another question here, could the tile size have been slightly bigger back in the day on the 8 megahertz Archimedes, or do you think David Braben picked the right tile size frame rate ratio? Well, I mean, when you play it on an ARM2, it's a reasonably good speed. It does get quicker on an ARM3 quite quickly. So to be honest, it could easily be bumped up for the ARM3 and have more tiles. But of course, it was written before any ARM2 machines were released. So and they didn't go back and up it. I mean, we discussed that it was in the learning curve, which is great, but it was exactly the same game as before. And even Zarch wasn't improved for modern technology. So for Lambda that came out on the original ARMs, I think it was the right ratio. I think it worked pretty well, because having extra tiles doesn't really change how you fire at things and interact with things. You are interacting with things in a fairly small playing area. What Big Lambda does is it makes it much more atmospheric when you're flying higher. It looks great, but in terms of gameplay and actually trying to destroy trees on the ground, it doesn't really make a big difference. And indeed, one of the one of the bits of feedback on the large version of Zarch that I saw on Stardot was that it made it harder to play, and actually didn't improve the gameplay. It just made it look amazing, which is possibly another reason why Braben chose not to go with the version that's in the micro user, because actually at the end of the day, this is a game and it's supposed to be playable, and having a massive landscape doesn't necessarily make a better game. So I think he got it right, but I think it would have been nice to add 2 or 3 tiles on each side for the ARM3 so that it played at the same rate and just had a bit more of it does feel a little bit like a spotlight on the landscape. When you compare it to Big Lander, it does feel quite restricted, but so a little bit would have been fun, but anyway, that is what it is what it is. And the fact that the binary for Lander that was bundled with RISC OS 2 is exactly the same as the Arthur one shows that, to be honest, Lander was parked at that point, and that's the end of Lander. It was all about Zarch then, and then that's more of a commercial decision. Do you create an ARM3 version that you then sell? Is it worth it in the marketplace? That sort of thing. By the time the ARM3 came out, was Zarch still selling? Were people interested, or had they moved on to, newer and bigger games? So it's a different sort of question at that point. Another question here. There's an object map which repeats. Yep. Could they be extended now we have more memory? Absolutely. I mean, it is just a 256 by 256 byte array, and there is nothing in the code to stop that from being extended. The great thing about ARM, of course, is that we're not restricted to bytes when it comes to registers. So the same question on the BBC would be, oh, that sounds a bit tricky, or you'd have to rewrite quite a lot. But to be honest, the object map, it passes in coordinates as bytes, so there's no reason why not. As words, sorry, it's those stupid words. So there's nothing to stop it. It wouldn't be that difficult to update that. But the thing is, I don't think people even realise that it repeats the object map, because it doesn't repeat over the same landscape. So it does feel a bit random still. And if you imagine the 256 by 256 original square, any water in there won't have any objects spawned on top of it. So out in the landscape, you get kind of big areas of greenery with nothing in them, and then clumps and stuff. So it feels very different. Even though it is the same map, it does feel different when it's applied to a different landscape. So, but yes, it definitely could. It wouldn't be that difficult. But I would challenge anybody to spot that was an improvement that was in there. So yeah. Has David Braben been in contact with you to discuss your work on Elite or Lander? No, he hasn't. I mean, obviously, he's very welcome to get in touch. It'd be great, but that's up to him. I have heard from Ian Bell. I sent him when I did the original, very first version of Elite, a cassette version of Elite. I did that, and it was all, hadn't done a website. It was just a Git repository, and all the comments and the deep dives were all in one source code. They were all in there. I then extracted them and put them on a website, but back then it was this massive file. So I sent that to Ian Bell, because he says on his website, if anybody else has analysed the source code that I've released, I'd really like to hear from you. So I sent it to him, and he thinks it's great. I also had a few chats with him over the NES version, which I've also analysed, which is an absolute mind-bending exercise in brilliance, because the NES is a tile-based sprite machine, and it runs Elite, which is a vector graphics game, which they thought was impossible, and actually it wasn't. And Ian Bell, I think, was probably the main coder behind a lot of the methods there, because by that point, David Braben was much more into Elite 2 and concentrating on Frontier at that point. So I think that's more of it's hard to tell. It is a Bell and Braben production, so I'm sure Braben was involved. But anyway, I had a few chats with Ian Bell about that, and he thought that was great fun. Somebody had kind of worked out how that worked and documented it. So he's been good. But no, I haven't heard from David Braben, but he knows where I am, I guess. Have I seen the ZX Spectrum version of Zarch? Yeah, truly amazing port. Absolutely, truly amazing port. I've only seen it on YouTube. I haven't actually played it. Don't have a Spectrum, alas. And I do have a ZX81, but I don't think that would manage to run Zarch quite so well. But I've seen it, and it's amazing. I mean, really, how? One of the reasons that Zarch, that Lander and Zarch work so well, of course, is that they're running on a groundbreakingly brilliant CPU, and the Spectrum. I mean, nothing wrong with the Z80. I'm not going to diss the Z80, but it's not in the same league as an ARM chip, and the fact that it even works is absolutely astonishing. Really impressive. I mean, it would be. There was a. I don't know if you remember. There was an April Fool article in Acorn User one year announcing a BBC Micro version of Zarch. Had a screenshot mocked up and everything. But that doesn't exist. But it is on the Spectrum. So yeah, wouldn't that be good if somebody decided to do a BBC version? I did think actually of taking Lambda and run it on an ARM evaluation system, because obviously it's in ARM 1 code, so it would happily run on a CoPro, and you know, hook it up to a BBC Micro and get it to draw the graphics across the tube, much like the 6502 second processor version of Elite. You know, that's something that may be possible, but you know, there are so many things on the to-do list. You have to stop somewhere, don't you, really? But, you know, maybe one day it'll be fun. But yeah, very impressive that the Spectrum version of Zarch is as good as it is. But Zarch is still the best version of Zarch. It was released as Virus for the Amiga and ST, I believe, possibly the PC, I'm not sure. And you see them side by side, and you really do see how brilliant the Archimedes version was. It's a really slick and beautiful game. I mean, Virus is really good on the other machines, don't get me wrong, but if you do put them side by side, and there are videos comparing them side by side, coming to the same conclusion that really the Archimedes one was mind-blowing. And the fact that it was developed before the machine was even launched is really quite astonishing. Really is very good. I think that's all the questions. Any others?
Any more questions you want to ask?
No.
Okay.
No more questions because they know everything.
Oh, one more. Do you still develop code on RISC OS? Well, I just developed Big Lambda. Did I develop that? Not really. I don't, but I have been a little bit. When I was doing the Ethernet Elite stuff, I did muck around with a scoreboard and client on RISC OS, because obviously it's all the same. It's a lot easier because you get lovely swicals that you can use to communicate. So a little bit, but not in terms of writing big apps on RISC OS. But I would like to resurrect my bouncy Jello thing and see if I can get it working on a Raspberry Pi, because it doesn't currently. Probably because it's probably got hard-coded screen addresses, and I'll just be able to do the same trick as with Lambda. But it's a delight. I mean, I fire this fella up a lot. He's my level 4 file server, so I'm always using RISC OS. I've got a BBC Micro here. You can't see them, in a master next to them, a little Ethernet network, and that's how I developed Elite over Ethernet. And having a really decent file server is really important. So yeah, I still use it quite a lot. It's a delight. Although the monitor's getting a bit flaky, bless it. It takes about 5 minutes to warm up, and if you switch it to a low res mode, it will start to go dark. So I'm not quite sure what's going on there. So I'm gonna have to look into that. But it's a workhorse, great machine. My probably that is my favorite machine I've ever owned, over the BBC Micro. But I have done most of the analysis, I guess, on the BBC Micro. So I've got a very soft spot for RISC OS, and that's not going to go away anytime soon. So who knows? Maybe.